You're listening to the FQxI Podcast. Today.
And, when that came out, everybody was like, whoa, that's just, amazing. It was just insane.
We continue our countdown of this year's biggest stories in physics.
It's wild. It's just, you get all these really funky shapes, and there's an area of instability, and then it breaks into pieces, and you get these sort of mini tornadoes. They actually refer to it as quantum weather.
As chosen by quantum physicist Ian Durham.
It would be like a bag of balls, and you put 3 brass balls into the bag, and you weighed the bag, and the bag weighed a certain amount, and then you took the balls out, and you weighed them individually, and one of the balls actually weighed more than the whole bag with the balls in it, which of course is completely absurd.
I'm Zeeya Merali. Hello again, and welcome to part 2 of the End of Year podcast series from the Foundational Questions Institute. As always, FQxI member Ian Durham, a quantum physicist at St Anselm College in New Hampshire, has joined me to pick out his top 5 results of the year. On the last edition, we discussed a couple of the runners-up that didn't make the list, including a very detailed conversation about one of the biggest physics claims made in the press in 2022, that a wormhole had been created using a quantum computer. If you haven't heard part 1 and you want to, you can find it on the podcast page, fqxi.org/community/podcast, where I'll also be linking to more information about all the advances that we chat about on this list. Now, it's been a very good year for physics. We will begin Ian's official countdown in this episode, but before we do, Ian, I believe you have a couple more items that haven't quite made your list. Take it away, Ian.
So there were 2 that I wanted to highlight as runners-up. The first is an obvious one that probably could have made the list. It's basically I had these 2 I had to choose from, and I went eeny, meeny, miny, mo. And that's the Webb telescope. Boy, you thought Hubble was amazing. The Webb is just insane. If you saw the Hubble's photograph of the Pillars of Creation, which is a very famous star-forming region, and, when that came out, everybody was like, whoa, that's just, amazing. And that was the Hubble one. And then the Webb one came out, and it was just like orders of magnitude. The crispness, it was just insane. What a triumph of engineering, and it worked this time, which is good because, of course, Hubble, they had to go up and fix it. It's good that Webb worked because, well, first of all, we don't have the shuttle anymore that we can repair it with, but also Webb happens to be at one of the Lagrange points. It's a point in space where it just happens to be a good place for an orbit, but it's very far away. So it's not like we could go service it. So it kind of had to work. Otherwise, we were in trouble. So the fact that it's working is just phenomenal. So Webb telescope, I'd love to make it one of the top 5, but I think the other reason is that it's not a specific discovery. It's a great engineering feat. It's awesome. I have no doubt that Webb will make some discovery that will make our list in the future. But for now, we're just making a runner-up and say, hey, it's up there, it's awesome, it's working, and the pictures are phenomenal.
Also, technically, didn't it go up last year? Just after our list, I think, probably. It went up on Christmas Eve or Christmas Day or something, or it was going to.
Our season runs mid-December to mid-December. I was thinking about this fusion thing that we're going to talk about later, and I was thinking about, maybe we should be like the Academy Awards, and that if you want to make my list, there's this deadline. You have to release your data by X date. Because the Academy Awards, if you want to get nominated, you have to release your movie by a certain date. Otherwise,
The first images came out this year, of course, so we can take that as grounds for eligibility, I suppose. I will put a link on the website, but I don't want to stir up more controversy because we've had enough controversy, but I will put up a link to some of the controversy around the name of this telescope, the JWST.
Yes.
James Webb, I think a lot of people have rightly pointed out, was not perhaps the person who should be glorified with such a huge honour. Yeah, and just so as not to be too coy about it, these are accusations of homophobia and just some horrible things that were going on at NASA at that time.
Yeah.
I know some of our members, Chanda, Prescott-Weinstein has written about this a lot, very eloquently, and it is certainly something that I think people are constantly debating and should be taken very seriously.
Yes, I agree. Many years ago, I read a biography of Webb that, of course, made no mention of this controversy. Recently, there was some pushback that claims that maybe he didn't have as much to do with some of these things as people claim he did, but I don't know. Either way, it was a shameful part of NASA's history.
So go ahead and read all about that. And we'll also see what links we can put up to some lovely pictures, but obviously you can just Google them, they're everywhere. And you can listen to our interview with science writer Mitch Waldrop from around this time last year, anticipating the launch, and discussing what the telescope could teach us about our universe. Next on your list, Ian, or not on your list?
This is a runner-up that probably could have made the list, but oddly it didn't make anyone else's list either. There were some physicists who, basically using some ultra-cold atoms, were able to observe this really cool thing where they basically behaved like tornadoes. And there are some really cool pictures out there on the web of this. They trapped and they spun a cloud of about 1 million sodium atoms using lasers and electromagnets, so standard for trapping ions. They spun them into these long needle-like structures, which is basically a Bose-Einstein condensate.
A Bose-Einstein condensate being this weird quantum state of matter that you can generate at ultra-low temperatures, where a group of atoms start to behave like one single atom.
Right, so you get bosonic behavior, which means that you can't distinguish between the individual parts. And so it starts to behave like this single entity that has all these shared properties in it. And in a classical fluid, if you were going to spin something like this, the example one of the articles gave was cigarette smoke. If you spin this thing, this vortex, it's just going to get thinner and thinner and thinner and thinner and thinner. Actually, if you look, sometimes you see these vortices in water, this long, thin thing, and the vortex just gets thinner and thinner and thinner and thinner as it goes. But of course, in the quantum world, there's a limit to how thin you can get. You can't spin it so that it's completely thin. In this particular experiment, they actually tried to push past that stage to see what happens when you switch from the classical thing, where you get these things spinning just to look like a nice vortex, to where you're now firmly in the quantum world.
We are, of course, adding links to the pictures on the podcast page, fqxi.org/community/podcast, and this will all make more sense if you look at those pictures.
And it's wild. It's just, you get all these really funky shapes, and there's an area of instability, and then it breaks into pieces, and you get these sort of mini tornadoes in there. And basically you have these crystals in there, and between neighboring crystals there are these dark spots where you have counterflow occurring. So you have flow that's sort of moving in the opposite direction, which is actually something that we see in all sorts of classical fluid systems too. They actually referred to it as quantum weather. I just thought it was a really neat thing, and the pictures were kind of cool.
The pictures are lovely, although I may be hungry because they're reminding me of noodles and at one point fortune cookies, which I think tells you that I am very, very hungry. But anyway, that was published in Nature. We'll put up a link. The pictures are great. I just want to pick you up on one thing you said. You mentioned that this is something you can see in sort of a classical effect as well. So how do we know that this is a quantum effect we're looking at?
So you calculate how far down you can go. Like, there's a quantum limit to the size of the sort of the needle-like, and I hate to make you hungry again, but like a long thin string of like spaghetti or angel hair pasta, they would say, right? So the long thin angel hair pasta thing. If you do the calculations, there's a limit to how far you can go down, because you don't have a classical fluid anymore. You have a Bose-Einstein condensate, and so you have to work with the equations for the Bose-Einstein condensate. It almost made my list, but alas, there were some decisions I had to make.
So here we are, finally at the list proper. What comes in at number 5, Ian?
We have a tie at number 5 between two particle physics experiments. One made a competitor's list, one did not. This is the one that did not make the competitor's list. There was some work done recently that showed that protons, at least probabilistically in terms of the way quantum mechanics works, can contain charm quarks. Now, what's bizarre about that is that a charm quark is heavier than a proton. So it would be like a bag of balls, and you put 3 brass balls into the bag, and you weighed the bag, and the bag weighed a certain amount, and then you took the balls out, and you weighed them individually, and one of the balls actually weighed more than the whole bag with the balls in it, which, of course, is completely absurd. But it's quantum mechanics, so, this stuff is kind of absurd.
How is this not number one? That sounds insane.
It's not number one because it's not unexpected in the sense that quantum mechanics is all about probabilities. The typical proton is made up of, I always get these confused. I think a proton is 2 ups and 1 down quark. And I think a neutron is 1 up and 2 down. But you can probabilistically, just like you can have, let's take hydrogen for example. Hydrogen is a proton and an electron. But there are other isotopes of hydrogen. There are isotopes of hydrogen that have, a neutron in them. Why do they occur? Because quantum mechanics says probabilistically, it says it's possible. That's sort of the nature of quantum mechanics. So quantum mechanics says typically a proton is 2 ups and 1 down, but there are other possibilities. Other 3 quark combinations. So it had been predicted the possibility that there was one configuration that included a charm quark, which are heavier than the proton itself. And what these guys were actually able to show is that less than 1%, but still a non-negligible amount of a proton's mass comes from quarks that are heavier than the proton itself. Now, how do you measure that? So you can actually see the quarks by, shooting stuff at the proton, and then you can get an image. And you can see the actual, 3 quarks in the picture. The other thing is you can just stimulate a proton to decay into certain things, right? So these guys, it was not an experiment, but it was like a meta study of experimental data that suggests this. So what they did was they used artificial intelligence to actually look at 500,000 proton collisions. If you slam protons into other things, you can collide and they could create different particles. This is sort of standard particle physics stuff. So they looked at 500,000 proton collisions from other experiments, and they found that there was a 0.3% chance that you would see a charm quark come out of the results, which is weird.
Yes, I'm just reading the article that we will be linking to on the website, fqxi.org/community/podcast. It's got a nice line here which says, "It's a bit like a very charming elephant spontaneously appearing in a room full of people whose masses, even combined, are less than its, but only if it quickly annihilated itself with an anti-elephant." So anyway, this was published in Nature. So we are having had a little bit of a discussion about Nature at the beginning of this podcast. We've been quite kind to them in terms of choosing other groundbreaking results that were published in their journal. But just to clarify on this one, so we're not saying that we have a particular proton that we can hold in our hand and put him on a scale and say he weighs this much, and then we break him down into quarks and we say that one of his quarks weighs more than him when we put it on the scale. It's more to do with probabilities and averages, or are we saying that?
Well, what we're saying is that there was, in all those experiments that they analyzed, there were a few experiments, 0.3% to be exact. So 0.3% of these proton collisions showed evidence of the fact that, yes, there was a proton that something happened to it and boom, you got a charm quark out of it. And so we are saying, it's a probabilistic thing, but it doesn't mean it's not real. It just means that it happens at an extraordinarily low percentage rate, right? People have a very hard time grasping the idea of probabilities. There's a much smaller percentage that you will roll a 2 on a pair of dice than rolling a 7, but it doesn't mean you'll never roll a 2, right? It's just that's the way probabilities work.
Yeah, but this isn't like rolling a 2 on a pair of dice. This is like, rolling a 59 on a pair of dice or something where, you wouldn't really think that it should be possible to happen at all.
You can imagine it in the reverse, okay? So imagine it in the reverse sense. Imagine you have a charm quark, which is heavier than a proton, and then you somehow take it and combine it with 2 other quarks to get a proton. Now, in order to do that, its mass has to go down. Okay. Well, according to relativity, right, E equals mc squared. So you're just giving off a huge amount of energy. The charm quark that's now inside the proton, you can't say, oh, but it's a charm quark, so it weighs this mass. Well, no, once it's inside the proton, it's not it's hard to say that it is a charmed quark anymore. I mean, it behaves like a charmed quark, but you now have this binding energy and things like that. The binding energy that's connecting it to the other quarks and things like that. It doesn't have its own identity anymore, right? So in bringing that charmed quark in together with some other quarks, you would just have to release a ton of energy in order to create that. So that in order for it to go the other way, you'd have to absorb a ton of energy, which is exactly what happened in the proton collisions. You have this huge collision of energy, and it's enough that probabilistically there's so much energy there, every once in a while, boom, there's a charm quark.
Okay, I believe you, and I believe the AI that made this discovery. So
Okay, so this is tied, by the way, because there's another particle of physics experiment that was also interesting. A Japanese lab discovered a tetraneutron, which is a 4-neutron particle. Very briefly, it forms as what's called a resonance. Basically, they collided highly neutron-rich nuclei with protons, but the particle physicists like to get this 5 sigma statistical significance. And that's what they got. And it answers this sort of long-standing question about whether you could have uncharged nuclear matter that could exist on its own. So in a nucleus, in heavier nuclei, right, you've got protons and neutrons. And as you get heavier and heavier and heavier, as the electrostatic repulsion between the protons gets greater and greater and greater, in order to hold the nucleus together, that's what the neutrons are there for. The neutrons are there to sort of counteract the electrostatic repulsion of the protons, because the protons and neutrons all interact via the strong nuclear force. But as the nuclei get larger and larger and larger, the electrostatic repulsion gets bigger and bigger and bigger, so you need more and more and more and more neutrons. But just to give you an example, uranium-238, there's 146 neutrons in uranium-238. 146 neutrons versus 92 protons, right? So you need all these extra neutrons just to counteract the repulsion. And when you get to uranium, it stops even working there because the repulsion is so much that you get chunks that break off. And so typically when the chunks break off and these things decay, you would think, well, okay, so, what chunks break off? So you've got this uranium-238. What happens when it starts to break apart? You've got more neutrons than you have protons. Can you get just a chunk of just neutrons breaking off? And typically we don't think that we do. You always have some protons that get broken up along with it. So there's never really been any evidence that you could just have a clump of neutrons just stuck to each other without any protons floating around. Now, I don't see why not from a theoretical standpoint. I mean, it's just a strong nuclear force. Again, it's a probabilistic thing. It's not highly likely, because if you do the calculations, you see that the likelihood of this occurring is pretty slim. So the fact that they found it, at least very briefly, you can get neutrons that just stick together without any proton around.
So they've done this for 4. They're going to look into whether it can be done with 6 neutrons or 8 neutrons or, however many more. I guess just the quick question then is, if they keep finding these structures, is that interesting beyond just, oh, it's weird, they've found, particles with more and more neutrons? Or, will this teach us something new about our understanding of the standard model, or how subatomic particles bind together? Or is it just, it's just kind of sweet and interesting that they can do this?
Well, I think it does tell us a little something about how particles bind and what kinds of things we can see. I'm just going to state right off the bat that everybody loves the standard model. The standard model, we've known the standard model has been flawed for at least 50 years. My entire lifetime, we've known the standard model is flawed. I mean, as soon as we discovered that neutrinos had to have flavors, right, and that, there wasn't just one type of neutrino, as soon as the solar neutrino problem came up, we knew the standard model was flawed right there, because the standard model predicts a massless neutrino. So I just want to emphasize, the standard model is a nice, beautiful thing, but it is not the Bible. Of course, I'm not a particle physicist either, but I do think it's important from the standpoint of like the charm quark thing, here's more evidence that, yeah, okay, quantum mechanics makes these strange statistical predictions, and yeah, they're not just anomalies in the math. They correspond to real things, that this stuff actually does occur. That's what I would say.
Well, there we go. That's the particle physics done for this list. Or is it? We don't know. No spoilers. But where are we going to next? I think you're cheating here a bit because you're making some of these joint winners, but then, technically we should be on number 3 next, but you're still going to be on number 4. So this is just your way of sneaking double the number of achievements onto the list.
I've only done this once. So that's the only tie. So number 4.
Number 4.
Yes, this is our condensed matter entrant. Again, oddly, this did not make anyone else's list. There is a result that came out earlier this year, an experiment that directly visualized superconductivity in a way that allowed them to understand a 35-year-old, I would say mystery, but prediction.
And this is specifically high temperature superconductivity. So in superconductors, electricity flows without resistance. Physicists have a picture for what's going on in materials that superconduct at ultra-low temperatures, close to absolute zero. But there are other materials that superconduct at a slightly higher temperature, and just how and why they do this is a puzzle.
So this is very specific. It relates to these things called cuprates. It has to do with the superconductivity in these cuprates. Superconductivity is kind of a weird thing, and there are a couple of ways to describe it. Actually, so there's an interesting model of superconductivity. Sort of imagine it as an electron sort of moving through. Of course, it takes the localized view of an electron. As it's moving through, it's like the lattice crystals. It's almost like they squeeze the electrons in a funny way such that they shoot through in a fast way. Of course, it's just a way of describing something. No one really knows what's going on there, right? But if you were going to think of it as on a semi-classical level, you could think of the electrons as like the lattice crystals kind of like squeeze it in this sort of undulating thing so that the electrons kind of shoot through in this way that is as if there is no resistivity, right? The vibrations that moves through a row of atoms sort of glue electrons together. I mean, this is sort of how it's described. And it basically, as it's shooting through, it's sort of drawing positively charged atomic nuclei toward it, and it just sort of sets off this ripple effect. And eventually it creates a Cooper pair, and a Cooper pair is a pair of electrons. So when we talk about cuprate materials, that's kind of what we're talking about. So then in the 80s, IBM researchers actually figured out that you could have a stronger sort of glue if you had sheets of copper and oxygen that were interspersed between layers of other elements. And they actually observed a superate conducting at 30 kelvins. So that's insanely cold, but it's much warmer than 4 Kelvin, which is where things were before then. I think they found them up to like 130 Kelvin already. But anyway, so this was sort of the birth of high temperature superconductivity. And Philip Anderson, the late Philip Anderson, Nobel laureate, had come up with this idea of just before high temperature superconductivity was really discovered, he said it had something to do with something called quantum super exchange. So it has to do with what's called antiferromagnetic coupling between cations. So cations are, so you have, if you remember your basic chemistry, you have cations and anions, right? Cation is positive, anion is negative. So what happened in superexchange? So you have these next to nearest neighbor cations that have an anion in between them. So a classic example of superexchange is you have manganese oxide. So it's an oxygen atom that has a manganese atom on either side of it. So there are two manganese atoms that are separated by this oxygen atom. And what superexchange is it's a quantum way for the manganese atoms to share electrons.
I was just going to say, I'm imagining them playing piggy in the middle.
Yes. Yeah. That's piggy in the middle. Yeah. Although it's very much a quantum piggy in the middle, right? I would think of it as the electrons are in a cloud, right? But the probability of one electron, its probability can be described as being in either of the two manganese atoms, but not the oxygen atom, right? So it's the superexchanges has to do with this electron being in these two different places. Anyway, that's the sort of the theoretical background. So what is this experiment? So it's this group. There's actually this one guy. So Seamus Davis. He's got like labs all over the world. Like, well, this is pretty amazing. This guy's got a lab at Oxford, Cornell, University College Cork, and the Max Planck Research Center for Quantum Materials in Dresden. I don't know if this guy like has cloned himself or something, but he's got labs all over the world. And he has basically tried studying these cuprates at an atomic level, and previous experiments sort of gauged the strength of the superconductivity by basically you cool it down, right, until you get superconductivity to begin. And the warmer the temperature, the stronger the glue that I described, right? And over the last decade, they've sort of refined how they can go about to propose this. And they've modified this scanning tunneling microscopy. A lot of people may be familiar with that. So it's basically you have this needle that drags around, you go over a surface and it just kind of electrons like leap from one to the other as you're dragging this needle around a surface. And so if you actually swap the needle's normal metallic tip for a superconducting tip, they actually measured a current of electron pairs rather than individuals. So their current, what they were getting Cooper pairs. So basically what they were able to do is map the density of Cooper pairs that are surrounding each atom in one of these layered things, right? Which is a direct measure of superconductivity. Now, this Nature was published in 2016. And so the important thing was this super exchange theory that I described, that Anderson had suggested. It's a theory. There was no evidence to support super exchange, but they had this particular cuprate called bismuth strontium calcium copper oxide, BSCCO, or BISCO for short, that they realized about 2 years ago would give them the properties they wanted, layer copper and oxygen atoms together to basically prove super exchange. The experiment was they took this BISCO stuff, right, which layers of copper and oxygen get squeezed into a particular wavy pattern. And that wavy pattern happens to be very conducive to proving this idea that Anderson had come up with, this idea that there are these sort of wavy things that occur from the oscillations in the ions. And then they use a scanning microscope to sort of check this.
So you can't see what all the hand actions that Ian is doing there to describe all the kind of waviness and the undulating that's going on in these materials. But we will put up links to articles and to the paper so you can see some of the images that hopefully will make a bit more sense. So I do have a question then. So it's surprising that this isn't on anybody else's list because high temperature superconductivity has been, a big mystery for a long time. I guess then that we already sort of knew what was going on with low temperature superconductivity. And then this is high temperature superconductivity. So I guess these two are not the same thing. It's not like, you change the temperature and suddenly a material that would have been low temperature superconducting becomes high temperature superconducting in a different way. It's just that these are two different phenomena that occur in two different types of materials with two different mechanisms in two different temperature ranges, and they just have the same sort of effect that we see, which is superconductivity.
Yeah, as far as I understand it, that is correct. So superconductivity, there isn't one mechanism for superconductivity. And truth be told, there are still a lot of unanswered questions in superconductivity, right? So yes, there are lots of different ways to achieve superconductivity, and this is one of them.
And I should also say congratulations to the proceedings of the National Academies of Science, or what is it, PNAS? What is it, the Proceedings of the National Academies of Science, or Sciences?
The worst acronym in the world.
Yeah, it does get made fun of quite a bit, but the Proceedings of the National Academy of Sciences, PNAS, for being the first publication, the first journal mentioned so far today that has not been Nature. So, well done for getting in there with that. And we shall come back and see if any other journals get onto the list apart from Nature and PNAS.
Yeah.
So congratulations to Seamus Davis in his superposition between so many different universities around the world, who carried out that experiment to visualize super exchange in high temperature superconductivity. Of course, we're adding links to his paper in PNAS and an article about his work. And I will once again take this opportunity to recommend George Musser's report on emergence, written for FQxI and the John Templeton Foundation, which I mentioned on the previous episode of this podcast. It has a chapter dedicated to condensed matter advances, and George does talk about low and high temperature superconductivity, although he doesn't quite get up to this result because he wrote it last year. So I will link to that too. Also, congratulations to the researchers who used the Riken Nishina Center's radioactive ion beam factory in Japan to create a tetraneutron, and the NNPDF collaboration for their analysis showing that protons may be more charming than previously thought. And to all the scientists and engineers behind the JWST and the quantum weather forecasters who are based at MIT. That's all we have time for in this episode. On the next edition, we'll get to the business end of the list and reveal the number one physics advance of the year. You can reach us on Twitter and LinkedIn at FQxI. You can reach Ian at Quantum Moxie on Twitter. You can reach us at FQxI Physics on Facebook, Instagram and TikTok. And I'm on Mastodon at FQxI at sciencemastodon.com. And Ian is there at Quantum Moxie at sciencemastodon.com. Okay, that was all a bit of a mouthful, and I'm a little bit tired after reading out that list. Anyway, till then, thank you once again to Ian Durham and to you for listening. I've been Zeeya Merali.